In this example, we're going to be looking for the power series representation of this following function. And for these types of problems, we're always going to start with a power series that we know something about, and we're going to use that as a stencil to help guide how we can get a power series representation for the function we're interested in. For this function that we're given up above, this looks like something over 1 plus or constants plus x type terms. And well, if we stare at this a little bit long enough, we might see that this kind of has the same flavor as a power series we know something about already, this 1 over 1 minus x. Now, of course, this power series that we know, it looks strikingly different than the function that we're interested in right now. However, when we talk about creating a stencil or doing composition of functions to find power series representations, what we're really thinking about is taking that power series we know, 1 minus or 1 over 1 minus x, and anywhere there is an x, we think about replacing that with basically open parentheses. So the idea being, whatever we put in those parentheses in the function, we can just put in the parentheses in the power series. So that's what we're hoping to get our function in that type of form. So we're able to use this kind of power series stencil. All right, let's start this off. So the first thing when we notice this function, well, in the function we're given, we have a 5x cubed in the numerator. But in the power series we're trying to drive towards, there's only a 1. Well, luckily, we can think about this using some just properties of arithmetic, like multiplication. And we can write this as a 5x cubed times 1 over 2 plus 7x squared. Okay. So now, at least, in this fractional term, we have a 1 in the numerator, like we have in that stencil. All right, so there's one mathematical move done. Next, what we can do is we see, well, in the stencil, we have a 1 minus something in parentheses in the denominator. Here we have a 2 plus our x term in the denominator. Let's try to make that leading 1 term by itself over here. So in order to do this, what we can do is pull out a 2 from each term in the denominator. So if we're pulling out a 2 or factoring out a 2 from each term, we have a 1 plus a 7 over 2 x squared. The reason being is if we distributed that 2 into the denominator, we would get back the denominator that we started with. So where are we at now? Well, we have 5x cubed over 2 kind of sitting in front now. And now our fractional term looks like 1 over 1 plus 7 over 2 times x squared. So now what we have is we have the 1 in the numerator like we have in our stencil. We have a 1 by itself like we have a 1 in our stencil by itself. But we're at this point now where in the function we're given, we have a plus. And in the stencil, we have that minus. And there's actually going to be a nice mathematical move that we can do here. In order to have that minus sign like we want it in the denominator, we can rewrite this as 1 minus, and then in parentheses, think about writing this as a minus quantity 7 over 2 x squared. The idea being, since we have a minus minus, those two things would be equivalent to just having that plus sign. So where are we at now? Well, we have a 1 in the numerator like we have in our stencil. We have a 1 in the denominator like we have in our stencil. And we have a 1 minus something in our stencil. And the whole other term here, we have in parentheses. So what we're going to be able to do in a moment is take what's in parentheses, the minus 7 over 2 x squared, and basically substitute it directly into the parentheses of the power series that we have. So we'll still have this factor of 5x cubed over 2 out in front, But now we can replace the 1 over 1 minus something in parentheses with that power series representation. So this is equal to the series n equals 0 to infinity of whatever we had in those parentheses in that denominator raised to the power of n. In this case, in that denominator, we had a minus 7 over 2 times x squared. So that is really a power series representation of this function, but we could take this one step further to practice some algebra and simplification here. So for right now, I'll leave this 5x cubed over 2 out in front. We have the series from n equals 0 to infinity. And now we have a product of terms all being raised to the nth power. Since we have a product of terms raised to the nth power, we could take each of those individual factors and raise them to the nth power as well. So first, we notice we have a minus sign. So we could write this as, well, one of those factors is a minus 1 to the n. Another factor then is a 7 over 2. We can raise that to the n. And finally, this other factor then is an x squared that we can raise to the n. All right, so one more time, I'm going to leave this 5x cubed over 2 out in front just momentarily, and then rewrite some of what we have. Now we have a minus 1 to the n. We have a 7 over 2 raised to the n. And since we have a quantity x squared raised to the n, we could write this as, well, x to the power of 2n. And now the last move that I'm going to make here is I'm going to take this x cubed and move it into the summation. So this is equal to 5 over 2 times the sum from n equals 0 to infinity of minus 1 to the n, a 7 over 2 raised to the n, times an x to the 2n, and also times that x cubed that I decided to take from outside of the summation and move it inside. And now since the last terms, x to the 2n and x cubed have the same base, vx, we can add their powers together. So we could rewrite this sum as 5 over 2 times the sum n equals 0 to infinity of minus 1 to the n, 7 over 2 raised to the power of n, times x to the 2n plus 3. And that could be a power series representation of the function that we were given at the start.